얘기를 하면서 너무 많은 의미들이 있었죠. 이것들을 하면 진짜 거의다 우리 프로젝트로 마셔서 이마이를 쓴 이사한 것은 이제는 어떻게서 가만고 어서 이거를 도시 있습니다. 인데스 허율 어떤 이벤트 지나가고 허율 선거 되게 돈돈 이해해주셔. 이하 어떤 디지털 디스플레이가 바로 나타나는 정도의 선택을 좀 가지고 나중에 이 제일 저도 상당히 되지도 쌤들만 잘 했었나.
Geometrie hierarchy command log project. Mana bakshana now the doctrine is a bit objects box. The problem of angle 되게 이거 아까 octave Cambridge에서 어떻게 되게 this complex max structure. 제가 먼저 알게 Oxford에서 다시 이거 doctrine가 맞습니다. 되게 거의 이제 그 doctrine 따라서 어떻게 되게 MIT에 그 computer unit 다 되게 힌트 거의 이제 벌써 되게 나는 어떤 이노이드 박 실자가 고란 디스트리뷰트 여자 assistant professor 같은 거라 티니스 같은 배운 거 알아보고 나서 싶었어요. 페이스북에 AI 리서치 그가 방향 어디 아크네이었던 거 쉬운 것처럼 제가 어떤 팀들은 뉴욕킹 어떤 살빈 해리츠 진짜 팀이 어떤 육수 다른 어떤 사이트 티저 이렇게 또 소통하는 친구들과 하는 컴퓨터 비전인데 어떤 저기 타는 팀 사업가시 크리에이션 이 어떤 딥러닝 퀴즈하고 이거 사이언스 플라이 제가 이건 어떤 딥러닝 AI 힘들 그 사업부터 들고 있었어 맞죠? 갖고 모든 맞고 인공 어떤 뭐뭐들이 접시한 같은 게 웨이트 다음 웨이트 그 하나들 예를 들면 컴퓨터 딥러닝 되게 어디 먼저가 신뢰 때 이렇게 무슨 딱티가 있어요. 이렇게 다음에 보시죠.
Thank you very much. So this is my first time in Mongolia, and it's very fun to be here. It's a beautiful country, and so I'm going to talk at a very general level about deep learning. So this is a topic which I worked with Sambayar for 5 years on, and we did some great things together. It's a great pleasure working with him. And then at the end of my talk, I'll talk a little bit about some things for the future. So this is kind of a high-level talk. Okay, so as some of you may know in the audience, there's been some very dramatic progress over the last 5 years or so on various tasks in artificial intelligence. And these advances have really come from one type of model, which is essentially a deep neural network, which I will describe in some more detail. I think there's been a lot of excitement in the media and the press about these advances, and I think but there's still many more challenging problems that need to be solved. So at the end of my talk, I will try and highlight some of these future directions that people are thinking about. Okay, but first, some history. So the idea of neural nets is in fact quite old. It originated back, in fact, in the 1940s. So there were people there who were exploring artificial neurons. So the neurons, of course, are cells in the brain. They were looking at how these could be implemented in synthetic form. And so they were building these giant connections of valves and these cumbersome circuits that could model them. And so the basic principle that they were exploring is something called connectionism. This is this idea that if you take a simple circuit and you connect many of them together in the right way, you can get very complicated behaviors arising. And this, seems to be the principle upon which the brain operates. And the question is, could they do these things with artificial circuits. So by simple operations, I mean the simple neurons they're exploring simply consisted of sort of additions and multiplications and summations, and maybe perhaps some kind of nonlinearity. So back in the 50s, things called perceptrons, which were really single-layer neural nets, were invented, and already with those they could do some very basic but quite interesting things. Now the problem was that they didn't know how to connect these models into more than one layer. Okay, and so there was nothing much happened in the 1970s, and then in the mid-80s, a variety of people, including Jeff Hinton and others, invented something called backpropagation, which is this way to train multiple layers of neural network together in a principled way. Okay, and that meant suddenly that they could actually, do many more interesting things with them. And then also at that time, people came up with special architectures of neural net, where the connections between the neurons were specially arranged, for example, to be very good for looking at images. Okay, so this is something called a convolutional neural net that was invented by Jan LeCun, who is also a professor at NYU, a colleague of mine, has worked with Sina as well. And so there was a lot of, they actually had a lot of interesting applications at that time. And then, for various reasons, people got interested in other learning techniques. And so, in about 2011 or 2012, people tried some very large neural networks on various problems in speech and vision, and realized that they actually worked incredibly well. And there was sort of a common set of ingredients to these performance that they achieved. One was these deep neural network models, which I will describe in a second. Also the availability of very fast GPUs, so graphics processing units, the things that normally people use for playing games. And then also big label data sets. Okay, so these models have many millions of parameters. We need lots of data to train them with. Okay, so this is going to be an important property, is that all these models are going to be trained in a supervised way, which I will describe in just a second. So I think one of the interesting things is, in many ways, the models are the same, more or less, as the 1980s, but they're just much bigger. Okay, and these, with enough data, and a big enough model, there's been a lot of progress. I should also say there has been, in addition to these breakthroughs, there has been some pretty exciting progress in other areas of AI, like playing the game of Go. Okay, so I'll talk about that briefly at the end. Okay, so just to talk about the data sets for a moment. So it took the community a while to compile big data sets, and so things like ImageNet came along in about 2009. So this is this idea they took many images from the internet, they got humans to label them, and this created a data set of about 14 million images, where they said what object was present in each image. Because you just had a single object that they labeled. And then more recently, there are other sort of data sets which are a little bit harder, which have many objects labeled, and so on. So anyway, these data sets were very important to the whole story. And then the GPUs, so one of the nice properties of these neural network models is that the operations within them are things like matrix multiplication, convolution, and these operations can be implemented in parallel very efficiently on these GPU architectures. And so this slide, I guess, so recent generations of GPU can produce about 10 teraflops of performance. So just to put that number in context, that's faster than the biggest computer in the world in 2000. And if you compare to the computers people were using for doing neural network research in the 1980s, things like Sun workstations, which probably you're too young to know what those things were. A single one of these cards is about 10 million times faster. Okay, so it's not just a little bit quicker, it's really many, many orders of magnitude more powerful. Okay, so with these things you can essentially run very big neural network models. And one of the this is a very famous example of one. So this was the paper that really demonstrated that these big neural nets could work very well for image recognition. So we'll look at it in more detail in a moment. So the idea is these models had many layers of neurons connected together. So in this case, about 7 or 8 of them. It had about let's see, about 60 million parameters. So these, in some sense, are the variables in the model that we're going to try and adjust during training. And they trained this thing on 1.2 million of those labeled images from ImageNet. Okay? And with training with 2 of these GPUs, it took them still a week to train these models. So you can see it's a pretty big, complicated model. And so this thing would just ingest the image, these are the pixels on the left-hand side, goes through all these layers of computation, and at the output it would come out with some prediction as to the class label. Now I just want to take a little moment to describe the, at a high level, just if you're not familiar with sort of machine learning, just how this works and how these deep models differ from existing approaches. Okay, so the basic idea is that you have an image like this, you have your model, and the parameters in the model are the weights in the layers of the neural network, and that input image is then processed through the network to produce some kind of prediction as to the label, say abacus. Okay, so in this case, the prediction is correct, we don't do anything to the parameters. Okay, now, that label, by the way, came from a human. Okay, so this is an important thing I will come back to later. So yes, the true label is abacus, it matches the predicted label, and you don't do anything. Now, if you take a new image, okay, like this, push it through the network, you get a prediction, zucchini, okay, which is a type of vegetable. Now, of course, this is not a vegetable, this is actually a little animal, called a slug. Okay, so this is not correct, and there's some, you have some user-defined error function that lets you compute the sort of how wrong the answer is, basically, between the two, and then you can use that error signal to go back and update the parameters in the model. Okay? And the idea is you do this sort of many times, through the millions of images, constantly putting them in, checking the answer they produce compared to the ground truth, and updating the model parameters. Okay, so you do this, over a period of days or weeks even, to adjust the parameters in that model so that they give the correct answer. And then what happens is, testing, you take that model, you present a new example, and hopefully it then gives the correct prediction. Okay, so one very important component here is that you can't memorize the training data. Okay, you must generalize to new examples you've not seen before. Okay, so that's the basic principles of what we call supervised training. Okay, so the crucial thing there was that we had that ground truth label slug that we could use to correct a mistake that the model produced. Okay, so now just to contrast deep models with existing approaches, so for many years in computer vision, the approach would be to take your input image, you would extract features, which is essentially a high-dimensional vector of numbers, through various hand-designed stages. So the key point there was that it wouldn't be trainable, and this would be things that humans thought would be good to extract, like edges, corners, these sorts of things. And then at the top, you would have some single-layer classifier, which did have trainable weights, that's the green box, and that would then, the mouse pointer, there we go, the green box, and that would then be used to make a prediction. Now the difference is, in the neural net, all the stages of the system are trainable, okay? So you can think of the neural network as each layer is extracting a set of features that are increasingly kind of high level and abstract. That means that, so initially, essentially down here, it's extracting something like edges, then things like, junctions of edges and stuff like that. And up here, of course, it's got sort of object level concepts. And then the final layer is just really the same, fulfills the same role as the green boxy edges of the classifier. Okay, so the key point is, in the deep nets, you get to train end-to-end the whole system. Previously, people just trained only this piece here. Okay, and that it turns out to be very important. It's a huge difference, and it tells you that humans' intuitions about how these systems should work are not that great. It's much better just to try and learn everything from the data. Okay, so just to quantify what's going on here, so this is a competition that's run every year. This is the year of the competition. Okay, and this is showing the error rate on ImageNet and the best performing model. Okay, so in 2010 it was 28%, came down a little bit in 2011, and then what's happened in 2012 there was this big jump in performance using the model I showed you just a moment ago from Jeff Hinton and colleagues, And then, perhaps even equally amazingly, in subsequent years, by refining the architecture of the neural network, the error rate has gone down even more. Okay, so this was actually 2015. I think the latest error rates are under 3%. Okay, so just to put these in context, it's a little bit of an artificial task for a human, but humans' error rates are around about this point here. Okay, and so the bars in green were conventional approaches with these hand-crafted feature extractors, and these ones in blue are all these deep neural network models. Okay, so it's gone essentially from this performance here is not useful in practical settings to something that works really incredibly well, and in some cases, better than human. Now, I mentioned the architecture had been changed. What's happened, in fact? Okay, so what is interesting to look at is the number of layers in the neural network model. Okay, so initially these ones, of course, really just have one layer. They're kind of shallow. These ones here, 8, 22, and then 152. So the idea is now that by making the models deeper, they seem to work a lot better. And so just to understand at an intuitive level why that should be, the idea is that each layer implements a nonlinear function. And when you compose multiple layers together, the decision surface that you can model becomes increasingly complicated. So with one layer, it's just a straight line. But with two layers and so on, it becomes now a much more complicated shape. And just to show you an example, so this is a little toy example here with some red and blue points. And we want to construct something that will classify or separate the space basically into the blue region and the red region. And you can see that with just a straight line, this is impossible. But with if you have 3 layers in your net, you can see that the surface, this purple line here, shows the decision boundary between the 2 regions. And you can see that you can implement actually very complicated separation between the points. Okay, so, and this is only 3 layers, of course. Now, this is also a simple 2D example. In practice, images, have millions of pixels, so there's sort of millions of dimensions, and so therefore you need to have many more than 3 layers in your model to be effective. But the state-of-the-art models can learn some very complicated invariances, and these are the sort of visualization of some of the features. So you can see that this is one particular feature that the model has learned in a sort of big ConvNet, and you can see it's finding sort of concentric circles, structures. And you can see that it's invariant to all kinds of the background color, the lighting, the exact position of where the circles are within the image, and so on. And this is another one here which just seems to like text on the side of objects. It doesn't really matter whether the text is big or small. It just somehow fires strongly this feature when there's text in the object. Okay, so this is a very nonlinear feature of the pixels. There's no way you could do this with a simple linear decision surface. Okay, so you have to have the depth in the model to be effective. Okay, so just to show you some examples. So this is a typical indoor image of an indoor scene. This is the output of a sort of state-of-the-art model. You can see it's identifying all the objects, putting a bounding box around them, and it has a little confidence as well, a score from 0 to 1, as to how sure it is about these things. Now, you can see it's getting most things. Maybe this is maybe that umbrella or something. You can see, even when there's a lot of occlusion, even when people are hidden, it's still able to do a good job. This is another example. You can see here very different viewpoints. You've got motorcycles from the side, you've got motorcycles from the back. You also have very different lighting conditions. You can see this is very dark, this is very bright, it still works effectively, all these things. Okay, so these complicated real-world scenes, the model is able to handle very well. And this is a bit of play. This is being processed frame by frame. So this is something where they're outputting a little skeleton on the person. Again, and you can see that it's able to sort of handle things when this is again not using any temporal continuity. It's just being processed independently. That's one. And this is another one that's a little bit harder. You can see sometimes it loses track and the person's in a very strange pose. But you can see in general the models are actually working really pretty well. Okay, you can see even it's finding like weird little people hanging out of the window. Okay, so essentially the performance of these models has gone from pretty hopeless to actually pretty good. Now that was the story. I told you the story for computer vision, But what's, I think, very amazing is that the same models, effectively, or very similar models, are being very effective in other domains. So in speech, actually, is a field which has been around a very long time. Performance has stagnated. They've not been able to improve significantly for a long time, using things called Gaussian mixture models. This is this approach here. And then along came the deep learning approaches, using these types of very deep neural networks, and they got big improvements in performance. So this is error rate here. This is word error rate. So the error rates drop significantly from the blue curve down to the black one, just using the thing. Now, one of the interesting thing as well to notice from this is that the traditional models, as you increase the amount of training data, their performance did improve, but not that much. Okay, so this curve is fairly flat. But the deep nets, because they have so many parameters, they keep getting better with more data, more labeled data, that is. Okay, so you can see that this black curve, actually the error rate keeps going down as you increase the amount of training data. So that's one very nice property. Of course, a lot of this does depend on having large data sets. So this is just an example. This is a few years old now, but this is an example of a system that Baidu, the Chinese equivalent of Google, use for their speech recognition. So this, you can see it's a huge model, 100 million parameters, 11 layers. It's trained on nearly 12,000 hours of speech. And this is some evaluation that they did of that against humans. So again, lower is better. So at least on these benchmarks, the system is getting comparable or maybe even slightly better performance on some of them than humans are. And then another domain, which I think is actually more challenging, is what's called natural language processing. So this is understanding written text. So the architectures there are slightly different. Instead of being a convolutional network, they tend to be ones, something called a recurrent neural net. And this is one that is able to model temporal dependencies. Which of course, when you're reading text, you have to remember the previous words in the sentence to be able to understand what it means. So this is, and one application there is translation. So in this case, they're translating from an English sentence. Economic growth has slowed down in recent years, and then they're trying to translate that into French. And the idea is that each word here is represented by a vector, a high-dimensional vector of numbers, and that's fed into this recurrent neural net architecture. And essentially, it ingests this input sentence, and then this is what's called the encoder, and then you have basically a high-dimensional vector which represents this entire sentence in English, and that is then passed to another neural net, which then translates it back into French. Okay? Now, at training time, they have labeled pairs of English sentences and French sentences. So they know what the target should be, and they can use that to use the same back propagation idea to train the model. And this is some metric here called a blue score, which measures how good your translation is. And this is, sorry, the axis is lost, but this is showing some of these quite dramatic gains, basically, in translation quality from these deep models. And so this green curve, I think, is the traditional approaches which were using sort of linguistic information. And in practice, these models don't know anything about grammar or syntax. They just try and learn directly from pairs of examples. So this is just English-German, but in practice, it's true in many pairs of languages where you have lots of data. Another example is actually what's called language modeling. So this is the idea of being able to sort of generate realistic text. So this is a metric here called complexity, which measures how sort of basically how good your text modeling is. And you can one sort of intuitive way to understand how good they are is to ask the model to just generate sentences at random. Okay, and you can see here that the sentences sort of make sense locally. The long-range scale is not so good, right? With even more new technologies coming to the market quickly during the past 3 years, an increasing number of companies must now tackle the ever-changing and ever-changing environmental challenges online. So it's sort of, that's kind of weird, the way it repeats itself. But that almost could pass for a real sentence. So this is just, and again, the story here is the same idea of these deep neural nets, just trained on huge amounts of data. This is actually, biggest models, again, are absolutely massive and trained on these huge data sets of text. So many of these models are very big, very difficult to do in universities, often done at places like Google or Facebook and so Okay, so the successes here have really been on these different domain areas of vision, speech, and natural language processing. So just to talk about some real-world applications, so just translation actually is a very obvious one. So you can actually take, yes, this is translating between, I think, English and Finnish. So Finnish is a very difficult language to learn. It's very not similar to many other European ones. So Google has, Google Translate works very well. Facebook also, because it does translate the comments that people make. So they translate between 40 different pairs of languages, and they do about 2 million translations a day, all using these deep nets. So this is one other nice property, which I didn't really mention, is that the deep networks are very easy to implement at test time, at scale. So if you're a big company like Google or Facebook, if you can only process a few hundred, examples, or if you can only process like, an example each second, that's not good enough. These models have to be able to run very quickly if you're going to meet the numbers that they need. So another example would be image recognition. So this is another thing which is super important, in fact, for big internet companies. So Facebook has about 1 billion images over that uploaded a day. Each of those goes through several neural networks. There's one that does face recognition. There's another one that does recognizes objects. And then part of that also looks at offensive content, so violence or nudity, things like that. And again, these are huge systems that are actually deployed in practice. And if your smartphone probably has some speech recognition in, so almost certainly that's using some kind of deep neural net to do that. Another application would be sort of self-driving cars. So everyone's very excited about these. The cars need to be able to understand their environment. They need to recognize the other vehicles and where the lanes are and so on. And that you have to do that very reliably, of course. And that all the current approaches use a lot of deep nets for doing that. I also should say that there's a lot of, these models I've talked about for things like speech and language, speech and vision, and natural language, but they can actually be applied quite successfully to many problems in the science. So there's a lot of interesting work on sort of, trying to understand various chemical structures, devise new molecules. People are thinking about how to apply them to genomic data. And in medicine, I think there's a lot of potential there for them revolutionizing healthcare. For example, recognizing skin cancer by looking for moles on your skin, screening breast cancer, also X-ray fractures and things like that. So there's a lot of I think applications more broadly that people are now looking at, because these models do seem to work very well. Okay, now I just want to talk a little bit more at a sort of high scientific level. So philosophically, what happened before in the old approaches was that the features that you would extract would be hand-designed. Okay, so by hand-designed, that means some researcher would sit there, playing around, seeing what they could get to work. Now in deep learning, the researcher is still in the loop, but all they're doing now, in some sense, is trying to design the architecture of the model. Okay, so it's not as if the thing is completely automated. Although I should say, actually, Google has some recent papers where they try to automate the architecture search, and it does provide some gains, not as dramatic as the gains from sort of good human architecture design. And one important point to realize here is if you just take a completely generic structure of a neural net, that is one that is all the layers are connected to one another densely, it does not work well. It's very difficult to train very deep, dense, fully connected networks. And so in practice what happens is that you have to kind of understand the structure of the signal you're providing to the network and have the appropriate architecture. So for images, the convolutional networks that I was talking about, those models exploit the fact that you have a regular two-dimensional grid of pixels and that there are local dependencies. Okay, so this pixel here tends to depend on its neighbors, but not on some very distant one. Okay, and those assumptions are baked into the architecture, essentially. And that architecture works much, much better than just a completely generic deep network of the same number of layers. And so these sort of inductive biases, as they're called, I think are very important to build into these models. And that's still something that is sort of done very, very easy. Okay, so one thing is that, so just to now, these models work very well, but there are some definite problems. Okay, so one big problem is there's no really good theoretical understanding of exactly what they're doing. Okay, so empirically, as you know, they seem to work very well, but we don't have a good mathematical theory that can predict when one model will work well and when it won't. And one of the big problems here is that the model is very non-convex. That means that there's many different sort of minima in the objective function you're trying to optimize during training. And so a lot of the mathematical tools that you would use to analyze these models unfortunately don't apply because of this non-convexity. Okay? So there's a very active, it's a big open problem in the field is how to sort of get a good, some theoretical insight into these approaches. So there are lots of very smart mathematicians and theoretically oriented people thinking about why these models work so well. Now, one other thing I should mention is that it's very hard to sort of understand a little bit what the models have learned as well. So you train this thing end to end. Somewhere in the middle of the model, it's extracting sort of useful features, but oftentimes there's no clear physical meaning to that feature. Okay, so that's in contrast to other types of machine learning model that people, look at things like graphical models, where each variable in those models has a very explicit meaning in the real world. And the sort of upshot of all this, you might say, well, what do you care? I think one of the things is that it's very hard to say why the model produces a certain output. So if you went to the doctor, and the doctor was using a deep net to look at your leg, which hurt, and the model says, okay, we should chop off your leg, then you would want to know, like, why does it say that, okay? Because it's obviously potentially a major thing. And so that's, I think, something that people are thinking about as well, how to deal with that. And then the last point, which I think is a very fundamental one, I'm going to spend a bit of time talking about, is the fact that you have to train these with labeled data. So in these settings, it's possible to, with a lot of human effort, to get millions of labeled examples, but there are many cases where you can't do that. Right? So one thing is that it turns out that if you look at our visual world, it's not like all objects are as common, right? So people and cars and houses and things like that, very common. But when you get to rare animals or like obscure objects like a tin opener or something like this, right? That's these things are much less common. And so practice, when you look at the distribution, this is a distribution here of the frequency of different objects in a sort of real-world database. This is log on both axes. So effectively what this means is you have a very long tail. There are many objects which are very rare. And this is quite a common phenomenon called Zipslaw. And so what it means is that there are many, many categories which are rare, and you only have a few examples. And so just to illustrate how extreme this is Wikipedia. This is looking at words. So these ones down here are telling you that the entire Wikipedia, this is log base 2, I think, so there's only 4 examples of that particular word in the entire Wikipedia. So it's not like you can get millions of examples of that given word, right? It's just incredibly rare. You need to be able to learn with just a handful of labeled examples. You can't have millions of them, like as I was saying previously. And so one of the big challenges then is how you learn in those settings. And this is called unsupervised learning, where you basically need to be able to learn without labels or maybe just from a handful of them. And so you need to be able to capture the structure of the data without necessarily humans sort of intervening and producing exact annotations. Okay, so that's a sort of practical motivation for why unsupervised learning is important. Here is a little biological motivation. So this is from Jeff Hinton. He's one of the sort of very famous people in deep learning. So he's making an argument that our brains can't possibly be using supervised learning methods that we're using at the moment. So he's arguing that this unsupervised learning, which I'm referring to, must be a kind of inherent part of human learning. So what his argument is the following. He's saying there are about 10 to the 15 synapses. So there's the connections between the neurons. You can think of those as like weights, equivalent to weights in the neural network. And we live only for about 10 to the 9 seconds. And so if you assume that you learn uniformly throughout your life, which is not true, you learn obviously much more at the beginning, then it means you have to be setting about 10 to the a million bits per second in order to adjust those connections. And if your mother, when you're young, she says, oh, this is a spoon or this is a plate, okay, but she says that just very occasionally. It's not like she goes, this is a spoon, this is a fork, this is a table, this is She doesn't provide labels the whole time. And so the question is, where do you get that information from? It's just not, there's not enough information in the information you explicitly get from your parents. And so the argument here, his argument is that the only source that's rich enough is the input itself. So somehow using the image itself and the sort of consistency of the image to be able to learn from. Okay, so for example, when you look at a bottle and you move your head, then the bottle stays in place and you can understand that it's separate from the background and things like that. So would sort of be, there's some kind of learning mechanism like that at play. Okay, so I think this is a super challenging problem. A lot of researchers are working on these unsupervised learning at the moment. We don't really have a kind of clear solution for it. Another point I think it's worth talking about here is, like you say, well, why don't we just copy the brain? Okay, most of us can do all these tasks that I'm talking about without really thinking. Okay, we can just, it's kind of effortless for us. Why don't we just copy that? Okay, so the argument is essentially a little bit like it's a little bit like people who were trying to build heavier than air flight, planes. Maybe 100 years ago, they looked at birds and they were like, well, maybe if I just put feathers on my arms and wave them up and down, then I can fly. And of course, that didn't work very well. And so I think the basic idea is that you want to be able to, if you understand the principles behind flight, the idea of an aerofoil, the differences in pressure, then you can instantiate that concept in different ways. So, for example, in aluminium and stuff like that, in an aeroplane. Okay, and so the idea is that our brains operate quite differently with quite different sort of hardware to computers. They have biological cells that operate quite slowly but in parallel, and then the computers are operating on these GPUs, which are somewhat parallel but generally quite serial. And so the idea is we have to be able to understand these principles behind sort of intelligence, the fundamental algorithm, and then we can implement them in different ways, perhaps on both machine versus humans. So we don't. So and the other point, I guess, which is the first bullet point here. I think the biggest thing, though, to be honest, is that we don't really have a good enough understanding of how our own brains work. So it's a very complicated thing. It's very difficult to get good imaging of the neurons. There are some exciting methods that are coming in the next few years that maybe it will help. But it's tough to understand, from the level of computer scientist, what it is you should be implementing in your model by looking at biological data. Okay, so I'll just talk a little bit more about some of the things that people are working on in the future, or working on right now, which I think are sort of future problems. So a lot of the stuff I've talked about is really about perception, about understanding, sensing the world, but it's, of course, that's one half of the equation, right? So that if you have an organism in the world, they need to sense, but they also need to decide how to move in the world as well. So there's this business, so we've been talking about this part here, but we need to there's also this whole piece as well, like how we decide what actions to take to make ourselves, to get food, to make ourselves happy and so on. And of course, the world is very complicated, and you can't afford to try out all possible actions. So what you need to be able to do is to predict which actions are going to be good. And this is really, I think, the sort of key point here, is this notion of building kind of predictive models of the world. So you need to give your machine some simulation of the world they can use to try out different possibilities. Okay, and then from those, it can then figure out which one will be the best. So just at sort of a little bit more of a detailed level, you have some sort of perception, machinery like a deep ConvNet, which tells you what you're looking at, and then you can try out different potential actions in your simulator, and that will then advance your sort of world state, in some way, and then you can try out another, then you have some critic that will tell you perhaps if that was a good world state or not, and then you can keep rolling this out. And this is all, inside the agent's head. And then once you try different actions here, and find a sequence of actions that seems to lead to a good world state, according to your critic. Okay? And the idea is that you would want to learn all these pieces, all the different boxes here, the critic, the actor, the world simulator, and so on, so in such a way that you can find action sequences that are good in practice when you try them out in the world. Now, the hard part is actually this green box, the world simulator. Okay, so in some cases, in some types of problems, you can build a good world simulator, So something like Go would be an example. It's a fully visible world. You can see where all the different counters are. It's deterministic. When you put down a white stone, it goes down in that position. It doesn't move around. And so in those settings, you can build out very good planning algorithms to decide on sequences of moves, which are equivalent to the actions I was talking about, that will lead to good outcomes, i.e. you're likely to win over your opponent. Okay? And so this was a very interesting piece of work from DeepMind, Google's DeepMind. And so what they did was to train, they were basically training these models that play against themselves. They were using a lot of the models I've been talking about, these convolutional neural nets. They would treat the board position as a kind of image, and from that they could come up with some predictions to whether a certain position was good or bad, and therefore which moves would be good or not. And they were able to beat, probably you've seen in the news, there's a lot of publicity around this, they were actually beat the sort of world champion Go player using these types of models. Now, of course, in the real world, you don't actually have full visibility, okay? And more than that, the real world is uncertain, okay? So if you have a tower of blocks like this, it's not quite clear what's going to happen, okay? There's many possible futures that could occur. And you might say, well, why don't we just use a graphics engine? That would give us a nice prediction as to what will go on. Well, one problem is you don't have to initialize the graphics engine with the current world state that you observe. That can be difficult. And the second part is to plan effectively, you need to be able to differentiate through this graphics engine. Okay, so normally you can't backprop through a graphics engine. And so people are trying to build neural net models that can sort of do simple prediction of various physical environments. Okay, these are obviously very toy settings, but they're essentially that world simulator box I was referring to. So this is what happens when you actually, when you run the real world, and it's obviously still happening inside a graphics engine. And this is the prediction from the neural net. So the neural net, you can see, it's not very sure where the yellow block goes, but it thinks it goes on the left side, and then the green block it thinks is somewhere on the right-hand side. So this is giving you some predictions to the future just looking at this initial frame. Okay, so and you could use this potentially for planning as to what would be, what would happen in the world. Now these are sort of toy environments. Obviously you'd like to do this for sort of real things. So this is, people then try to do this with video sequences. So this is just a video of a robot arm pushing objects around on a table. And these are essentially different generations from a model that is predicting what might happen. Okay, so this is essentially each of these correspond to different action sequences that you give this, world simulator. And when it's in red, these are completely hallucinated video frames. And you can see that it's able to sort of simulate the arm moving in a reasonable way. When it does, sometimes when it touches the objects, they get a bit fuzzy. So that's sort of, it shouldn't do that. That's kind of a mistake. And this whole thing is trained on supervised. So if you can train up a really good model like this, you could use it to plan how to pick up an object on the table. So that's the kind of where a lot of people are heading to with this kind of line of work. Okay, so a few minutes, I'll just briefly mention a couple of things. So one other thing we haven't talked about is, in the brain, we do have structures that aren't represented in our existing models. So for example, memory. Okay, so most of us have, we all have a structure in our brain called the hippocampus, which we use for storing information over the long term. And the neural nets I was describing don't have an analogous structure. So there's been quite a line of work on trying to add that to existing neural net models. So this is something called a memory network. This is actually some work from Sambayar that we worked on together. Has proven actually quite a successful model that people have built on in quite a way. And the idea is you have a sort of neural net over here. This is a recurrent neural net on the right side. And the idea is that this is able to access a memory store, okay, with some sort of addressing operation. It can read information which you can use to incorporate when it's updating the hidden state of the model. Okay, and you can have multiple accesses before you produce an output. You can train this whole thing sort of end to end. So if you have some sort of output, you can backprop not just through this part here, but also through the memory storage mechanism as well. And this is one possible architecture. People also thought about these. This is an RNN here with a stack. So this is a sort of standard computer science stack where you push and pop items onto the stack. And so you can use these types of architectures basically to do kind of interesting things. So this is one little example from Sambayar's papers where you give it these little toy stories, and it has to do simple reasoning. So the computer reads these sentences, and then you ask a question, where's the milk? Okay, and then the machine predicts the hallway, and that's actually correct. And when you look inside what it's doing, you can see that it's attending, it's using this memory mechanism to retrieve different sentences within the story that are relevant to answering the question. Okay, so this way you can train these models actually very quite simple sort of reasoning properties. Okay, even though there's no kind of formal logic here, just with the neural net, you can do interesting things. Just one, before I finish, just one sort of other example where you can use these models is sort of personal digital assistants. So this would be something that could help you, book a restaurant or make a flight reservation. A lot of companies are thinking about these things, Microsoft, Google, Facebook. This is something which realistically probably you're starting to see already, in fairly limited domains they can work quite well, and as time goes on they'll be more general and able to handle more sort of unstructured types of things. So the idea is you have to sort of have some knowledge about the world in some database, you have to be able to model the user, that is you, what you're thinking and what you want, and then you need to understand sort of, how a machine, you need to understand the spoken commands from the human. Okay, so you have to understand the natural language they're using. And this is a little example of, this is not designed for booking a restaurant, this is just having a conversation between a human and bread and one of these memory networks. This is a sort of, a downstream version of the thing that Sino worked on. And it actually has some personality to it, so it tries to sort of pretend it likes certain things. So you can see here, this is the first person, this is the human asking questions, and you can see that it's giving fairly realistic answers in natural language and so on. So it's able to carry on, these things are able to carry on somewhat realistic conversations with humans. I mean, they're still a bit weird if you look closely, they kind of give slightly off weird answers sometimes. I'll skip over that. One thing I just wanted to say, if you're interested in all this stuff, there's lots of great, one of the nice things about this field is the barrier to entry is very low. So there's lots of open source packages for programming languages for doing this kind of research. PyTorch is one example that is developed at Facebook. All the research papers that people produce are available online for free. You don't have to pay anything for them. And a lot of the data sets you need for this research are also available online freely. And so it's something where the barrier to entry is fairly low. You don't need a giant particle accelerator or something like that to be able to make progress. Okay, so just to summarize, there's been a lot of progress on these perception tasks, like vision, speech, and so on. I think there's a lot of active research on how you might tackle more advanced AI problems. And there's a lot of, so these are sort of hot problems, I guess, that people are thinking about. Unsupervised learning, how you build these predictive models of the world. Communication, both between different agents, in some environment, or between agents and humans. That's something people are thinking about. And I think just the final point I would like to make is that some people in the media are making all these very dramatic claims about what we can do with AI. I think a lot of that work there's a bit too much hype. So because there are really still many fundamental unsolved problems that we don't know how to address. And so I think there's no clear timeline for us having true AI. So all these movies about how the machines will come and kill us all is really science fiction. There's no real basis in fact for these sorts of things. Okay, so I'll stop there.
Lots of different people around the world thinking, as you said rightly, the machine's going to out-do us. They're going to kill us. They're going to basically control all over the world, control us, our minds. What do you think about that? This is my first question.
Okay.
Second question is, in terms of natural language processing.
Yep.
So in terms of, for example, when I use Google Translate to translate from English to Mongolian,
Yep.
I've got lots of different incorrect or quite laughable
Yes.
translations. So
Yeah.
my question is, how do we improve this kind of translation methods
Yeah.
and accuracy
Yeah.
where we, for example, Mongolian, when we go online, when we pause, when we chat online, we don't really use our own alphabet, we use anglicized version, so we use
Yeah.
the Latin alphabet.
So
when it comes to that, how do you translate?
yeah.
Make
Okay.
it like
Sure.
that?
Okay, so I can answer. The first one is, unfortunately, the thing you're referring to there is really, I think, more of a science fiction concept. I don't think any serious AI researcher worries about these things. This is why the media, I think, is a bit, crazy at times. I don't know why they pay so much attention to some of the people who talk about these things like singularity. So if you see how clumsy and bad a lot of the methods are at the moment, it's just, it's a completely, there's no, clear timeline for reaching the sort of true AI you would need for these types of things. So the first thing really is, the answer to the first part is, this whole singularity thing is really a science fiction concept rather than a scientific concept that people worry about. Now, to your question about the Mongolian translation, so that's actually a very interesting point. So now, one of the big problems of machine translation at the moment is, if you have a common pairs of languages, like English to French, there's tons of data, okay? So in Canada, they use both languages, the parliamentary proceedings are all in both languages. Now, the problem you hit with Mongolian is you don't have that much parallel text of, carefully translated English and Mongolian. This is what's called a low-resource language pair. Now, there's a lot of very interesting research that's happening at the moment, actually in the last year or so, on this type of problem. And so what's fascinating is how you go about doing it. I think there's going to be quite a lot of breakthroughs, actually, in the next, probably you'll see operating in practice in the next year or two on this. So the big data, so the reason translation is bad is not the fact that you're anglicizing the words and not using Cyrillic, it's the fact that you just don't have enough sort of parallel pairs of sentences. So that's the tricky part you have to overcome, and I think there'll be a lot of progress on it. It's actually fascinating how it works, the techniques that will probably deliver this breakthrough, which is that they don't use any paired languages. They build models just in Mongolian, just in English, and then they learn a mapping. They learn how to map. So they learn to map between the two languages from a relatively limited amount of training examples. And so that most of the structure is built kind of using just a single language. That's a very quick explanation of how they are trying to do it. So I think it's a good question, but yeah, that's hopefully will fix things a bit. Yeah.
First of all, thank you very much for your talk. I have one question. We can see that computer vision is closely related with deep learning. So can you see that computer vision is the basis of deep learning? And would you recommend to learn it first?
That's a good question. So I think it's true probably that deep learning is most dominant. That or speech, I would say. But deep learning has completely taken over those fields, and nobody basically uses the old techniques anymore. I think the nice thing about when looking at vision for deep learning is it's very easy to sort of inspect the models and see what they're doing. Okay, you can plot images of the results of the model. If the model's having a problem, it's easier to visualize, intermediate output and get some sort of intuitive feel for what's going on. I think it's a little bit harder on some problems like NLP, or even speech actually is also a little bit harder. So it's just easier to debug things when you can visualize stuff. And I think vision gives you that advantage. So in that sense, I would say that's the easiest one to start with. And it's also true that there's a lot of resources online, like pre-trained models that you can just download and use and stuff like that. Perhaps more so than the other domains. So, yeah.
I tried some of your models from a site like Apple. They're like Korean models for actually machine learning datasets, and I tried it and I realized that some of the applications are recognized objects due to the two-dimensional, and I thought that maybe if it was like three-dimensional, it would recognize objects very instantly, more accurate. So you say that people are using lots simulation to actually train these models. So in order to achieve that three-dimensional understanding of the object, can we use a simulation to actually train it?
So that's a good question. So I think the question here was about getting a 3D understanding of the object and whether we could use computer graphics engines to simulate an environment from different viewpoints and from that train data. So currently the models don't have any explicit understanding of 3D. There's nothing in there that, and in fact, what's interesting is we don't either actually. So if I show you an object from a very unusual viewpoint, that you're not used to seeing, you also will struggle to recognize it. So I don't have an example on my slides, but offline I can show you. So the answer is yes, you can use the simulators. I think one of the big problems is the simulators are very good for giving you a diversity of viewpoint. One of the big problems is that if you want to build a system that can recognize real objects, you need many, many different types of, say, chair. Right? So if you recognize chairs, you need to have hundreds and, literally thousands and thousands of different types of chair. And in the 3D world, there aren't that many 3D models available online of chairs. So what happens is your model ends up overfitting to the few hundred 3D chair models that you can download online for free, right? And then, so practice, it doesn't work as well as you might think. That's the big problem, typically. So, when you go to the internet, right, you can get millions and millions of images of chairs. So even though, you're not seeing each one from a whole bunch of different viewpoints, just collectively over the full million, you will end up seeing a lot of different views. Sure.
Thanks for the speech. You mentioned that it's an end-to-end process for different for neural networks. So what would make a good data scientist? As you said, because it's an end-to-end process, it seems like you just need to feed the data, feed the rate data, and then it will work itself out. So what is this human involvement there? For good data scientists. Well, you mentioned architecture of the model, right? But besides that, there's anything that good data scientist stands out, working with neural network.
Yeah. So because I guess you're asking about sort of, So obviously, what you mean by data science is itself perhaps a little bit, can be interpreted in many ways. I think one factor is, of course, in practice, presenting the data in the right way to these models is very important. So the pre-processing in it. So, for example, removing various, mean or some correlation in the data before you present it to the network can be very important. I think one aspect that's also important here is that the models often are very certain of their prediction. And so if you're trying to give a sort of, if you're using this in a real setting, it's knowing how reliable the estimates of the models are is quite important in practice often. And so the current models have no mechanism for that. So there's a kind of outer sort of machinery you want to build, which way you could assess the accuracy of these deep neural net models that you've trained. So that's something like, from a scientific point of view is important. Yeah, I mean, the deep nets, I guess, you could view them as just a way to kind of, go from the raw input domain, like pixels or the speech waveform, to some sort of high-level feature representation. And then what you do with that is more part of then the sort of process of being a data scientist, whether you're trying to build a classifier or you're trying to build a regressor of some kind or some other type of some variable of interest or something like that. Yeah, sorry, slightly. Yeah.
I have 3 questions. First one is, there's a website where you include music and it tells you the name, and I'm wondering about how it works. And second one is, how do data scientists, as for k-nearest neighbors, how do data scientists assign k values and choose a best preprocessor? I just finished course on EDX, so I'm confused.
Okay, so the first one, the music recognition system, actually, you don't need any fancy machine learning. It turns out that if you just look at various sort of sequences of notes from a tune, those things can end up, if you have enough of them, they form a sort of unique hash key, if you like, which you can then use to index into some database of known music. So there's because tunes are there might be some slight change in the absolute pitch of the notes, but the relative changes often are fairly well defined, and that, so there's no sort of uncertainty in some sense that you need to model. So when you're trying to model a cat, cats can look quite different to one another. Whereas if it's a particularly famous song, the song's the same no matter where it's played. So it's a much easier problem basically. So that's how they work. Basically, they construct a hash function from the waveform. And then you're talking about how you select the optimal k and k-nearest neighbors. So that's a sort of model validation type thing. So typically you'd have a validation set of data that's held out on your training set, and you would use that to try out you would train models or use your k-nearest neighbor classifier on sort of, for 1, 2, 3, 5 or something like that, and see how well each one of them performs on this validation set. So then you would use the value of what's that distribution.
저도 상만이 아니라 진짜 재밌게 아소타였던 분들이 되게
болохоор моделууд нь бас бизнес сургацсан датаас бүгдээр бэлэн байж байгаа. Харин шагналаар монголчууд багтдаг юм учраас миний value араас үнэтэй бас нэг апдейт хийхгүй чаг гэж тэмдэглээд аль талаас нь хахад бүрсний хэлбэр гэдэг тэр чиглэлээр хийсэн байна. Тэгээд нэгэд тэнцээс бол энэ анализ хийх сайтаас юмсан жил гэсэн тийм объект хийх байгаа хийсэн. За тэгээд бүгдээр болохоор бүршгэж хааж бидний 970 тоног тат бүрээс наваа. This networks iOS хатдаг standard хэрэглэнээс энэ зүйлсээ тэгээд цэцээр зүгээр хийсэн жоохон бодлоо. Тэгээд болохоор дүрс тос бүрний аны тэмцээ хийх болмын зургаантай. За тэгээд уртандаа бидтэй болохоор арт-чарн байгаа. Тэгээд нөгөө сургалтын файлыг хэлбэр болохоор ингээд хэлбэр зургийг хэмнэл тэгээд тэмдэглэлийн хоёр үзэсгэлэн тавьна. Тэгээд амжилттай байна. За тэгээд энэ ретинанит болохоор BaseNet болон нөгөө feature pyramid network гэсэн. BaseNet болохоор маш олон фейстэй хүнсгэлсэн тэгээд ерөнхийдөө 50-аас дээш фейсүүд явдаг. Ерөнхийдөө нэг код network feature pyramid network нь болохоор нэг зургийг ингээд олон хэмжээгээр олон скейлээр гэсэн тус бүрт нь тааруулдаг. За тэгээд энэ архитектур нь болохоор BaseNet дээр Convolutional Network яваад дараа нь feature pyramid Facebook-ийн офис тэмдэглээ хаан байлгах бас тэмдэглээ ямар төсөлтэй болох юм та тийм зүйл байна. За тэгээд сүртэй юм ашигласан бол тенсор керас ретинанит юм болон утсан ашигласан. Тэгээд ಈ хугацаа багаас нь 40 бохоо background resource моделлаараа REST тавилжээ. Тэгээд теста тэгээд 7 цаг хугацаанд сурч үлдсэн байна. За тэгээд өөртөө энэ яахан бороо эхний бороо цэвэрхэн явчаад тэгээд зүр засч байгаа тэрнээс өргөжлүүлээд явсан болохоор график жоохон офсын уушааг ажилласан байна. Тэгээд эхний 24 цагийн хийчихсэн. Тэгээд шатнэр сургалтын өглөөр шалгал нэлээд өндөр. Тэгээд нөгөө дараа нь шалгалтын хүчээр шалгахад жоохон багсан юм болохоор сургалтын хавьд цэжсэн байлтай харагдаж байгаа. Би илүү өглөөр нэмээд удаас өгөөд үзсэн байна. За тэгээд амжилттай бас үргэлжлүүлээд бол юм байна. Тэгээд энэ дээр 50-аас дээш хүртэл хамарсан зүйлсүүдийг хэрэгжүүлсэн байгаа. Тэгээд тэр validation өөртөө 50-аас дээш хүртэл явах юм хөвчтөн шагнаадаа зөв хэмжээ гаргаж байгаа. За амжилтнууд нь жоохон нэг шагаад зарим дээр нь олон батцсан юм өөрөөр. За тэгээд энэ болохоор богино хугацаанд сурсан болохоор жоохон өөрхөн муутай байсан. Тэгээд энэс цааш нь өглөөний мэдүүлээ тэгээд янз бүрийн REST-тэй цаашаа 100 ч юм уу параметруудаас болоод сургууль илүү өгөхтэй. За ахад гэсэн.
Одоо яг нэг тавыг засалж байгаа байхгүй. Тэр хооронд асуултаа хариулсан. Тэгээд сод хариулт байх зүйл чинь. Тэгэхээр энэ хэдийн төсөл маань энэ глобал компани Монгол хөгжүүлэлтийн компани систем техник компани тэр компани нэрмж чангалыг хийж байна. Тэгээд шагналыг нь одоо захирал нэг хоёр боллоо. Нөгөө хоёулаа
길 장구하게 대충 시작하고 유로 거기를 시작하다가 많은 간반이 좀 엄청 있었고 얘는 되면 이게 그거 알아서 시스템이 이렇게 막 시스템 테크닉 목적이 이렇게 있잖아 안스테이스 있잖아. 아, 그 안스테이스를 올라와서
힘이 daha hani hocuk tadında sosyal erkek gibi 그 소산이 거기에 이렇게 정말 모이게 어떻게 해야 되니? 그렇게 아까 들었죠. 되게 약간 밑에 올수도 힘이 더 약간 이렇게 되게 수도 사이에 나서 근데 일단 합자가 이렇게 또 어떻게 약 영어 분이 얘기를 듣고 있었는데 오링 사운드 스틱도 사는 것을 되게 상식도 상가 되게 자기 더 들어야 돼. 맞습니다. 이들이 조금 스틱이 많아. 자, 되게 비슷한 거로 지금 맞점세 남았사한테 거의만 가는 난 어디 저번사하고 이런 사번사에 나오고 무의식 매트마틱에 보이는데 잠깐 말했죠. 이 기억은 유비 거의만 가는 난 점에서 안 쉽다 어찌 자랑의 뿌리 이때는 내 다시 그런 단에 세트 도스탄 안스텐스테 컴퍼니 내부체 장애 도스탄도 어른스도 비주 어서와 마순점인 멘트 자, 들어봤대 미중
자, 맞다. 어떤 것은 그 조금이라도 더 쓴다고 쓰자고. 그러니까
Okay, so I'm going to talk about graph neural networks, and this should be sometimes when people talk about graphs with respect to deep learning, they mean a different kind of thing. They mean a computation graph, which is just in general, it's a tool for actually running code. We're going to talk about something different. It's a neural network that eats a graph as input. So first, let's start with some kind of a review of common neural network architectures that are classical now that people use for lots of different things. So there are really good architecture types for certain kinds of data. So for things with translation invariance and things with grid structured data, so for example images or audio, people use convolutional networks. For things that have a one-dimensional causal structure, in other words, there's a notion of time and there's a notion of past and present, and you should not base your decisions based on the future, you should only base it on the past. You have things like RNNs. So when you have a 1D ordered structure. I think by the way, I think my slides are, I think it's compressed, but it's not going to be a problem yet. I don't think it's actually covering the whole thing, but okay. So for general kind of fully connected feed-forward networks, so this is kind of the first time someone shows you a neural network, it's usually this thing, a fully connected network. These things are less successful. They have not actually worked as well as the other things. So what is a fully connected feed-forward network? So let's see, can I, yeah. So we do like this, let's see if I can, yeah, let's try. There we go, great. Okay, so what's a fully connected feed-forward network? A fully connected feed-forward network takes in a vector, a fixed size vector, and outputs a different fixed size vector. And the way
it's
okay, so fully connected network eats a fixed size vector and outputs a fixed size vector. And the important thing about a fully connected network is that each coordinate has a specific meaning. The order of the coordinates in the vector that you feed the fully connected network has to be the same for every vector. So you guys have seen, some of you have seen a bunch of stuff about deep networks, but just for review, to make a deep network, you concatenate or you compose a bunch of functions like f0, f1, all the way up to fk, where each fi or each fj takes in the previous, the output from the previous layer, multiplies it by a matrix, and runs some nonlinearity on it. This is kind of the most classic neural network. Now, when A is just some matrix, this is a feed-forward network. If there's no other structure present. So the most general form of this kind of network with no multiplicative connections is called a feed-forward. And usually people optimize A and B for, some past. This thing is the most general form, but it doesn't work great. So even though deep networks have been extremely successful, it's convolutional networks or RNNs or things like that that have been very successful. Fully connected networks have not been very successful in the sense that you can optimize them and they do something, but almost surely if you have a problem and you try and use a fully connected neural network on it, you will not get the best results you could have. Something else would have worked better. And the reason is you're not taking any advantage of kind of the structure of your problem. Your problem probably has some structure, and if you just toss a feed-forward fully connected network at it, you're not taking advantage of that structure. The structure of the problem is important. So someone previously asked Rob, oh, well, what does the data scientist do? I mean, the deep learning can do everything, right? It just eats all the data and trains itself. And so it's right now, at least in our current with our current technology, it's far, far, far from true. The design of architecture is super important. I mean, to be honest, to answer that question, the data scientist munges data. I mean, messing with data is by far the most important thing. Like the actual input, arranging, and Rob touched on this, arranging and collating and manipulating the data is the most important part still. But you can't just throw a feed-forward network at something and expect it to do great. On the other hand, ComNets work really well for images. Why do ComNets work really well for images? Because ComNets work on grids, and we use properties of the grids to make ComNets work. We know images are roughly translation invariant. What does that mean? By the way, it's roughly true. It's not exactly true. But if I take an object in an image and I shift the frame, the object is still the same object, right? Or you have translation invariance in the sense that if you're detecting something, if I shift it over, the detection is shifted. So you have translation invariance for detection, for recognition. You have translation equivariance for detection. And that comes from the group structure of the grid. The 2D grid is a group, or the 1D grid is a group. It's a commutative group. It's a very nice group. So group there is in the mathematical sense, the algebraic object. So grids have translation variance. Grids also have a multi-scale structure. And I can take an image, for example, and I can subsample it by 2. And I roughly still have the same things in the image. And that being said, when I subsample, I throw away some details about the image. If I took a picture of some trees and I subsampled it, maybe you couldn't tell the leaves as clearly, but now I can still see that it's trees. So I keep high-level information, I throw away some fine details. That multi-scale structure is, again, very important for images and is understood by the ComNet. So ComNets work because they understand the structure of images well, because they've been designed to match the correct invariances of images. Graphical neural networks are an attempt to have something like a ComNet, but for more general things, for graphs. By the way, there's one other thing I want to say about this. When you have a convolutional network, so if we looked at a feed-forward neural network, each coordinate had some specific meaning. And if you look at the matrix that defines a layer of a feed-forward network, everything is connected to everything. That's what fully connected means. In a convolutional network, you have parameter sharing. Again, coming from the translation variance, specifically gives you parameter sharing. You have a very small filter that runs over the entire image. And instead of having to have something, let's say an image is 128 by 128 by 3 that you would feed in, you don't have a filter of size 128 by 128 by 3, rather you have a filter of 5 by 5 by 3 or something like that. So a tiny fraction of the total number of parameters you would have for a fully connected network. Okay, so we want to do the same thing, but we want to input a graph. We don't want to just use the grid graph. So the ComNet is kind of like a graph neural network where the graph is a Euclidean grid. Here, we want to, at test time, dynamically eat a graph along with some vectors on the graph. So, again, what is a graph NN? A graph NN is something that you give it a set of vectors and some edges between those sets of vectors, we'll say weighted edges. And the graph network has the correct weight sharing to process that kind of structure. So this is kind of an old idea. I'm going to say goes back to at least Gorey, Maffardi, and Scarcelli in 2005, but if you look, there's hints even farther back than that. But people didn't use these things for a long time just because we didn't have the kind of, nothing was working well enough to justify this. But now, actually, deep learning in general is working better than it used to, and in particular, GraphNN is working pretty well now. So some things that people have used it for. So let's say I give you a social network, or part of a social network. We want to find a vector representation for each node and edge in the social network. And a social network is a kind of graph. It's a you can be connected by, if I'm friends with you, then we have an edge between us. Or you can have more subtle things, like if we both liked the same thing. So for example, this paper here, the Hilton 2018, is on Pinterest. So these guys are actually at Pinterest, and they have built this sort of model to embed every single pin. In other words, to get a vector representation for every image at Pinterest and every user at Pinterest. And so users are connected to images if they've put that image on their board, or if they think you might want to put that image on your board. So embedding knowledge graphs in databases. So knowledge graph or a database is a thing of the form. So for example, you have Rob here. Rob was born in England. You can have a bunch of facts about people. Rob Fergus is an object, and you have a relation born in, and England is an object, and you want to kind of find some neural representation of Rob Fergus was born in England, Arthur Schlom was born in the United States, and maybe the United States is a country, and England is a country, that sort of thing. So people have, the edges are given by the relations, and the nodes are given by the object types. So you might have multiple different kinds of relations, multiple different kinds of edge types. People have used these for graphical networks for designing molecules. So the graph is the different kinds of, the nodes are the different atoms, and the edges might be the bonds between them. And then Saya has built a controller for many interacting agents using a graph NN. So these things are actually working now. They weren't working a few years ago, and it's pretty cool. So before we can eat a graph as input, we should be able to eat a set as input. So the thing about a graph is it's permutation invariant. There's a set underneath. And so if we can't deal with a set, so a set, remember, is permutation invariant and has dynamic resizing. In other words, if you want to eat a set, so when we talked about feed-forward fully connected networks before, you eat a vector. Your network eats a vector. It has to have fixed coordinates. And what is happening here? No, I don't want to do this now. Okay. So if we thought about feed-forward networks from before, each coordinate in the vector had a fixed location. But in particular, the input was a fixed size. If we want to eat a set, we have to accept that the set at input time might be different sizes. So we need something which is invariant permutations and is able to dynamically resize. The simplest thing, at least that I can think of, might be your idea of simple is different, but for me, the simplest thing that you can imagine doing to a set of vectors that kind of respects permutation invariance and dynamic resizing is to take a mean. Right? So if I have vectors v0 through vk, and I take the sum of all of them and divide by k plus 1, then that thing is completely invariant with respect to permutations. I can flip the order of the things, and summing them doesn't change anything. And it's invariant resizing because I've divided by the number of vectors. So the mean is the kind of prototypical thing that is invariant with respect to dynamic resizing and permutation. So the mean is an operation that respects the structures of sets. The same way that a convolution is a kind of a thing that respects the structure of grids. We can, of course, replace the mean with any commutative normalized mapping, but mean is kind of a nice thing to think about, so we'll start there. And by the way, before you think about, oh, I need to do a graph NN or something like that, if you actually try this stuff, if someone gives you a problem where you have graphs or sets, the first thing you should do is take a bag. Just take a mean. The word bag here is bag of word embeddings, bag of embeddings, whatever. That bag in this parlance is usually meant mean. Okay, and you should try it because means are really simple and often are very powerful. But sometimes you need something better than a mean. Sometimes you need something more powerful than a bag. So here's a thing that you can do to process sets in a more powerful way than just take a mean. You can take a mean multiple times. So first I'll write it in equations. Then I will show a picture. Then I'll write it with matrices. So we'll say the same thing multiple times. Actually, let's do the picture first. So we want to do a thing to eat a set which is more powerful than taking a mean. And by the way, I have to point out, this picture is sinus. I stole it from it. That's how it goes. But it's a nice picture, so we'll use it. So what we want to do is, we want to do something more powerful than just take a mean. So we have, say, an input to our machine is a vector at each of these nodes. So each of these are the nodes. And what we'll do is, we will find some function that pushes straight through, and some function that compares what happens when I push straight through, and with what happens when I take a mean. Right? So instead of just taking a mean, I'll look at what happens over each location in this thing with what happens when I take a mean. So in equations, it looks like this. Instead of, can you see the cursor? You can. Okay. So what we'll do is, at each location, so hi corresponds to a node, we're inputting a set of vectors at the bottom of the network. And in each location, what we're going to do is we're going to have some function of what I have currently at that location and the mean from everybody else in the set. And then we can parameterize that, for example, in a simple way as just h times what I have at my location, and c times whatever I have as the mean, and then pass it through some nonlinearity. So, and here c again is the mean. So let's look at the picture again. We start with a vector, we start with a set of vectors, so this is the first vector and this is the second vector, but again the order doesn't matter. And we have some function right here that eats the mean and the vector at the location. And we iterate, well, they could have different ones at each layer, but the point is that you do something much more powerful than just a mean, because you get to combine the mean with the vector at each location. So you get to essentially communicate between the elements of the set. If you write everything in matrices, this looks like a fully connected neural network, except the weight matrix has this special structure. Everything on the diagonal is h's, and everything off the diagonal is c's. And so this is, again, you can see from this matrix view that this is dynamically resizable, because these c's are normalized. Here we've normalized them so that it's dynamically resizable. So if I make a bigger input, I can just expand this matrix and it behaves exactly the same way. But otherwise, it looks like it behaves like a feed-forward network, except that it's dynamically resizable and its permutation invariant. Okay, so let's look at a video of this in action. So this is this kind of structure being used to control a bunch of cars. So here, the cars don't know what they're doing. They're kind of lost. So I want to point out this is science work. So now they've all been trained. But the nice thing to notice from this video is there's a different set of cars at every time step, but there's only one network controlling them. So there's a swarm of cars. You can see all the cars that are on there, but the actual controller doesn't care that things come in and things come out. So if you imagine, again, our feed-forward neural network, you had one vector, and you push that through the model. You can't add a coordinate at test time. You can't change the list of coordinates as you're going. With this kind of model, you can dynamically, at test time, resize the input. Okay, so now we did sets. Now let's actually work on graphs. So what's a graph? A graph is a mathematical object that has two things. It has a set of vertices, and in this talk we're going to be working with weighted graphs. So you have a set of edge weights. So if you have n vertices, you have up to n squared possible edge weights. Maybe some of them are 0, so we throw them out. But you have n vertices, n squared edge weights, and so that wij is kind of covering that edge. Maybe that's that node is node I, and that node up there is node j. And that tells you how strongly is node I connected to node j. We can talk about functions over the vertices of a graph. And what that just means is you have a set of vectors. Again, remember before we were talking about sets of vectors. Now you have a set of vectors. Each vector lives over one of the vertices. And those vectors are connected by weights. Again, the weights wij. Let's ignore that. So now we can actually finally introduce a graphical network. What's a graphical neural network? It's exactly the same thing as before, but now instead of taking a sum over everything, instead of taking just a plain sum over everything, we take a sum where the weight is, where the sum is weighted by the edges in the graph. Okay? So just like before, we update kind of the vector at each node by some function that depends on the vector of the node and the kind of mean, or the communication from the other nodes. And that communication is just given by the weighted average of the connected nodes weighted by the graph weights. So this is kind of the simplest form of graph neural network. And what you can see is that this has a parameter sharing. In the same way that a convolutional network has a parameter sharing, the parameters only depend on this f, so the f theta is kind of everywhere on the graph it's exactly the same. So in the same way that on a grid, you have these little filters that move over the locations and have the same weights no matter where they are, here, this f works the same no matter which node you're at. So you have the weight sharing that respects the structure of the graph. So we can show the same thing as before. So here is the same one, but now this is a slightly more complicated example. Now this one might use a graph. So before we had one neural network that kind of averaged everybody, but here what you might have is the graph connects everybody that's in this intersection, everybody that's in this intersection, everybody that's in that intersection, everybody that's in the intersection up there. So again, this is a dynamic object because at each step, who is here is changing, and who is over there is changing. So the power of this model is it's eating the graph at test time. It doesn't eat the graph, you don't have to train it with a fixed graph. Okay, so now what we did before was write kind of the simplest form of graph neural network. We can actually talk about a slightly more general form of a graph neural network. And here, what we've done is, instead of hi plus 1 depending on just one of just the weights and the nodes, we can look at all the powers of the weights. So this kind of model was introduced in Kipf and Welling. It's more powerful because here W0 is just H, W1 is the averaging C. You can add more powers to H. So this is a strict generalization of the previous thing. If you know a little bit about graph theory or spectral graph theory or harmonic analysis, this starts to have a really cool interpretation. If you take a graph and you look at higher and higher powers of it, let's say it's normalized appropriately, then higher and higher powers of it correspond to kind of working on the Fourier space of the graph. And so this kind of construction, as you make it big, in some sense you can think about it as running a ComNet, but on the spectral side. By the way, in the same way, people usually use ComNets. When people usually use ComNets, they have very small filters that are run over the image. Because of the properties of the Fourier transform, you can run a ComNet completely on the, well, at least the filters you can run on the spectral side. You can take the Fourier transform of an image, and you can pointwise multiply by the Fourier transform of the filters. And when you have this kind of more powerful version of a graph ComNet, you get something that looks like that, where you're operating on the kind of Fourier transform on the graph. So let me skip that. Okay, so there's all sorts of things you can do to that you can do to make the thing even yet fancier. So you can decorate the edges with types. What does that mean? So before we talked about embedding a knowledge base, right? And in a knowledge base, you might have a relation of the form person, born in, country, but you might have another relation of the form person, likes, animal, something like that, right? And so for each relation you have a different kind of edge. So the graph NN has no problem with that. You can decorate the edges. You can add a different weight matrix for each kind of edge, right? The same thing works. You can decorate the vertices. Again, you can have different types of vertices. So maybe you have some special operation you want to do if a vertex corresponds to a person, and a different special operation you want to do if a vertex corresponds to an image, if you're Pinterest, for example. You might not want to treat people and images the same way. Again, you can just add something to the node processor. There's a more powerful version of those ideas that is getting more and more popular, called an interaction network. So an interaction network is a graph neural network where you work over all pairs of things. So what that amounts to is, instead of having a fixed weight matrix, use a weight matrix that's dynamic, just like the computation is dynamic in the graph. So, for example, you can use some weight matrix that's a function of the ijth node. So a really simple example is you take, that should be a minus up there, e to the minus, sorry, no, let's do it like that. You can have, that should be normalized. So you can have a really simple example is you say, well, let's look at the inner product between the two nodes. If the inner product is very big, then the weight between those two is strong. And we will look at it like that. So this technique lets you not only have a fixed weight, but you can have a dynamic weight that's introduced at test time in the same way that you were eating dynamic sets at test time. These were studied in Vertex et al. It's a DeepMind paper for predicting physics. So you have a bunch of physical objects running in a simulation, and the interaction between them is measured in this way, and kind of everybody, all the objects talk to each other through the graph neural network, and you get a prediction of how the whole system of objects is going to behave. Neural message passing, another example where this kind of structure was used, and that was for drug design, for building molecules. What properties will this molecule have? So interaction networks are really powerful. It's kind of not only is the input to the neural network dynamic with the graph, but the graph can be dynamic within the processing. There's all sorts of other kind of bells and whistles that you can add as you kind of fool around with this kind of architecture. You can do skip connections from the very bottom all the way to the top. You can have multiplicative interactions between between updates, and you can have different W's at every layer. Anyway, the main point is that a graph NN is a network where the update rule depends on the local structure of the graph, and the parameters are shared in the same way a ComNet shares parameters across different locations in an image. Okay, so we talked about graph NNs. We talked about ComNets. Now ComNets work on a grid, which is some kind of set. And we said a graph NN is kind of like a ComNet but on a general graph. So let's actually look at what would happen if we did the basic GNN construction that we talked about before, but on a grid. Okay, so what does a GNN look like on a grid? Well, it depends on the grid. But let's pick the standard 2D grid, right? So a standard, in mathematical terms, a grid which is like Z2. And let's pick a weight matrix that's a local connection. Let's say each node is connected to its 8 neighbors, something like this, right? So if you have a graph which is the standard, I said d-dimensional lattice, but let's just say 2D lattice, and let's say the weight matrix isotropic filters here, let's say is the 8 nearest neighbors, or the include yourself is the 9 nearest neighbors. So if you have such a graph, and if you have and it's a grid like this, then the GNN looks like a ComNet, but every single filter is isotropic. In other words, it doesn't have edges. Every filter looks like just a bump. So that's kind of a crappy ComNet, frankly. It's not a good ComNet. So why is it so much less expressive? Why is this GNN construction so much less expressive than a regular ComNet when we just take it like this? Is there a guess? You're not allowed to answer. So someone who's not him or Rob, any guess as to why is it that this is so much less expressive? So ComNet, here, let's draw a picture. So a ComNet can have a filter that looks like this. It's maybe plus over here and minus over here. It has big values on this side and small values on this side. But when we use this GraphNN construction, every filter is radial. Every filter looks like this. It's terrible. You would never use this for image processing. It's not good. So we said, oh, this is like a ComNet on a graph, but somehow it seems a lot more limited than a ComNet, than the ComNet is on a graph. Is there any guess? Okay, so the reason is the grid is a very special graph. It's a group. On the grid, I know what this direction is. The notion of right makes sense. The notion of left makes sense. The notion of up makes sense, and the notion of down makes sense. These are things, and they come from the algebraic structure of the grid. Right? It's not, this graph is a very, very, very special graph that has very special extra properties that a general graph doesn't have. So if I have something that looks like this, what's up at this vertex? It doesn't.
There's no direction.
There's no definition of up. There's no definition of right. And so we can't, there's no way we can get a notion of edges if you have the most general construction. So a GraphNN in the most general setting, because we've made a very general construction, it can't be as powerful on kind of specific instances. Now that being said, you could make it so that a GraphNN has a notion of up, down, left, and right if you knew it. And one way to do it is to use decoration. So we talked before about things you can do to a graph, things you can, bells and whistles you can add to the GraphNN construction. Well, you can do a vertex decoration. If I decorate the edges of a graph with its kind of xy coordinate, then the function that eats that, node xy, now it can understand what left and right is. So if you have extra information, a graph is a very general, very, very, very general object. If you have extra information that lets you know what right or left is, you can add that to the construction very easily. And you could get back something like a real comment. So kind of there's a little moral to the story, which is if you give an object X structure, you can't expect it to understand more than X structure. It only kind of understands the amount of structure you've given it. But a good construction can allow you to add more structure, and this does in fact do that. So let's see, how much time do I have left? I have like 10 minutes left? Okay, so I want to compare GraphNNs with something that you hear a lot about now. If you are kind of practicing, if you want to practice using deep learning, so especially in text, the current state of the art on text is what's called a transformer model for most tasks. Transformer is an example of attention. So attention is also a thing that works on sets and could, in fact, in some senses, be made to work on graphs. So I want to compare attention and the GraphNN, the construction that we've made. So attention is a weighting. We talked about bags as kind of the simplest thing you can do, taking a mean as the simplest kind of thing you can do that respects a set structure. Attention is another thing that respects a set structure. And what is attention? Attention is a dynamically weighted bag. It is taking a mean. Here we're taking a mean over the vectors in the set, but there are weights in front of the thing. So instead of having weights of 1 over n, which is what you normally do when you take a mean, you have weights that depend on some input. Okay? So a kind of standard choice is soft attention. And soft attention usually means softmax attention. And what that means is the weights that you use for taking the mean are something of the form softmax of the current values. So, or softmax of the inner product of some query with the So the notation here is terrible. This should be a Q, not a C. Something like that. This is a really bad notation. I apologize for that. So the weight should be something like a softmax of the vector at each node with some query vector. So softmax is kind of a nice, more powerful version of taking a mean. It's a dynamic version of taking a mean. And kind of a nice example of how you can use attention in an actual model is a memory network. So a memory network is, in some sense, a simple version of just using attention to do all computations. So what you do is you have, just as before, you have a set of vectors. And in addition to the thing before, you have a controller with a hidden state. So you have a set of vectors and a controller with a hidden state. And what the network does is it updates the hidden state by doing self-attention, by doing attention over the things in memory. So in pictures, what does it look like? You have a set of vectors as input. Again, just as before, you have a set of vectors as input. You take the dot product of all these vectors with some query. You take a softmax, and that softmax gives you weights, and use those weights to make a weighted sum, and that gives you the thing that you use to update your internal state. So this network architecture was first described by Jason Weston and collaborators in 2014, and Sina made this actually work. So in Jason Weston's version, everything was hard attention and it was hard to backprop through. Sina made this actually so you can backprop all the way through. The transformer is kind of this recent version that introduces multi-headed attention. So in a moment, we're going to talk about more or less parallelism. The difference between a memory network and a graph-NN, at least in the simple cases that we've described now, is you can think of a graph-NN as a purely parallel processing, and you can think of a memory network as a serial sequential processor. And transformer is some kind of step towards being slightly more parallel. It uses, instead of having one attention head like this, you do this k times in parallel, and then you combine them with the neural network. Combine the results with the neural network. So here was how kind of the attention works. You actually, a memory network does multi-hop attention. So in equations, you fix some number of hops, you input the set of vectors, and we showed what a internal state update. You find the attention, you update the hidden state based on a weighted average with the attention, and then you repeat. Right? So we showed kind of the inner loop, and now we're showing this outer loop of you start with the input, you do the attention as before, like as I've shown in the previous thing. You use that to update the hidden state, and you repeat. So the transformer is yet another kind of more complex version of this, where instead of addressing with one attention head, you do it k times in parallel. By the way, a lot of these things are just out there. Like, they're pretty complicated if you wanted to do everything yourself. But you can go online. If using PyTorch, for example, there is a memory network model, there is a transformer model in Vertex. So you can just go and download these. And if you have some natural language processing task, you can just toss them in. Like someone has written this thing for you. They're very powerful models, and they're just there for you to use. So to conclude, let's say this thing. What's the difference between attention as a set processor and kind of this graph-NN version of a set processor? Well, we kind of said it, but let's look at the picture. The picture is we look at when we do one hop of self-attention, you do something like this. You look at everybody. Since you do a softmax, you pay attention essentially to one of them, and that one of them you use to update the hidden state. Whereas in the graph-NN type version, you pick a bunch of these, everybody gets processed simultaneously, you communicate and then push everybody out, and then you repeat. So a graph-NN at its core is a parallel, at least the way we've talked about it, this simple graph NN is a kind of parallel processor, whereas a memory network is a sequential processor, or self-attention is this sequential processor. And I'll stop there because things get complicated, there's not much. So I'll stop.
Thanks for the great talk. Just to give us a question. So you came from like math background, you did your PhD in math, and now you're doing AI. Do you think it gives you an advantage, or is there any benefit from all the skills?
So there are definitely some advantages. There's also disadvantages as well, right? Because I would say the #1 skill that a kind of AI person should have, at least nowadays, is to be a really good hacker. You should be able to munch data, you should be able to crush through computing. That's super important. That being said, as a researcher, having a math background is super important. If nothing else, nothing else, because lots of people will write papers saying, oh, this is the theory behind why something works, and it's not really usually true. And so it's much easier to see that with math background. Specifically with respect to, I think, convolutional networks, my background is in the mathematics of signal processing, and I think in terms of understanding how ComNets work, and in the end, it doesn't give you necessarily a technical advantage in making them work in PyTorch, but in kind of understanding how they work, I think there really is an advantage. But as a day-to-day practitioner, it's not obvious that having a math background is kind of crucial. Having being a good hacker is crucial. As a researcher, it's definitely a useful skill set.
Hi, thanks. Steve, lots of things to process. Just one very simple layman's state. Could you tell us the real-world use cases where you can use GNN, CNN, and also NNN?
Right, so RNNs are typically used when you have sequential causal data. The word causal means you have a notion of, you have an ordering, right? So if I think about the English language, it's not completely true that there's an ordering, but roughly there is a time ordering in the way you speak in English. The thing on the left, the thing on the right depends on the thing on the left much more than the other way around, right? Another example is time series. If you are measuring, if you have a controller for, let's say, the heat in a room, you want to make a system that controls the air conditioning, right? There's definitely a causal order. You need to make your decision based on what's happened, and you're going to predict. So for this kind of structure, an RNN is a really sensible choice. It's not the only choice, but it's a very sensible choice. So ComNets and self-attention can be used in that situation as well, depending on your exact setup. A ComNet is used when you have a grid. And specifically when you have a grid and you expect some degree of translation invariance or translation equivariance. What does that mean? That means if you shift the thing, it's the same after you shift it. And you expect some sort of multi-scale structure. In other words, you expect that as you apply lots and lots of layers, some more abstract things come out. So if you have these two things, then a ComNet makes sense. So images are the classical example, but audio is really common. Audio is often processed with ComNets as well, and more natural language is processed with ComNets as well. If you think about it, the trade-off between an RNN and a ComNet in natural language is an RNN has theoretically infinite memory, although in practice it's not true. A ComNet has a fixed width that it works over. But a ComNet can be anti-causal. It can see things in the future and work them backward. What people do when they use RNNs is they run an RNN going both directions over a sequence, which is kind of a complicated thing. Now, when do you use attention? Or when do you use a graph NN? Well, use a graph NN when you have a graph, specifically when you have a dynamic graph. Again, a graph NN is a much more general construction than a ComNet. A ComNet is very specific. I have a grid. A graph NN is when you have a dynamic graph of test time. So an example might be like from Sina, where you're controlling a swarm of agents. and agents are coming in and out of the swarm. There's no way you can, there's no kind of permanent grid you can make on these because some of them are gone, some of them are, you know, there the next day. Sorry, some of them are there at one time step and not there the next time step. So the grid is dynamic, or the graph is dynamic. Attention is more finicky. I would say that historically it's a thing that was good for some question answering tasks. Recently, because the transformer has been so successful, it's starting to be that a lot of natural language processing is actually better with a transformer than it is with an RNN or a CNN. And that is actually self-attention, but it's a very kind of well-tuned self-attention for NLP. So that being said, the particular transformer architecture requires you to do all sorts of hacks to kind of, in some sense, the vertex declarations like we talked about, what they call position encoding, to kind of get back the causal structure. So, yeah, I would say that you look at the structure your problem has, and you pick the model that has as much, you try and put as much of the structure that you can take from your problem. You try and put as much in the architecture as you can.
What is the worst case of graph structure in?
What do you mean, the worst case?
Worst case.
Like computation? If you mean the worst, how expensive these things are. The graph, so the graph has n squared, and if there's n vectors, it's n squared in the kind of worst case in the computation. But usually people use sparse graphs for large things. So this starts to be, you know, if you think about it from an abstract computer science, like theoretical computer science perspective, it starts to be really different than in practice because most of the time, if you have n large, you use sparse graphs. So the asymptotic complexity is like number of non-zeros times number of entries in the times n, which is not terrible. But actually doing sparse matrix vector multiplication is much slower than dense matrix vector multiplication on most machines. So the kind of, you know, abstract computer science-y version of complexity is different from the practical complexity. The short version is GraphNNs are a lot slower than ComNets or even fully connected networks on most modern machines because GPUs love big, dense matrix multiplications, and these things require, you know, some fudging to make that happen. That being said, if you look at, for example, the FAIR-seq implementation of the transformer, which uses multi-hop self-attention, which might be slow. Actually, it's well implemented, and it's not that much slower than an RNN, for example, in practice. So the thing is, when you ask what's the worst case complexity, the worst case complexity can be bad, but someone coded it well, and you know the constant is small, and you end up better. So unfortunately, there's not a good answer. It depends on your problem.
So we're running out of time, so we're going to take maybe one more.
Okay, when you have a data and you know that there's some causal relations from the forwards to backwards, and then you suspect that there's some backwards to forward special relations, and what would you do? Did you have some case?
You can use a bidirectional RNN and especially if you know that the relations going this way are different than the relations going that way. Mm-hmm. One thing you can do is build an RNN that kind of looks at whatever it is that's going this way, and have a separate RNN that's looking at whatever you think is going that way. You can also just try ComNet and see what happens, like see if it can unify the two things. Mm-hmm. But basically, if you know that there are two kind of separate directions, I would just put those into two separate RNNs, going the opposite directions.
Okay, great.
Okay, so thanks for the really exciting talk.
бид нар болохоор RNN модель ашигласан. Тэгээд RNN модель болохоор энэ Machine Learning гэдэг нэг DevOps гэдэг конференц юм уус дээр танилцсан. Language Model TensorFlow гэдэг энэ моделийг ашигласан байгаа. Тэгээд энэ модель болохоор зөвхөн англи хэлтэй текстийг уншдаг. Тэсний энэ болохоор гэрэл наадад тохиолдоод 5 хатны дөрвөн монгол текст уншдаг. Тэрэл монгол текст уншдаг. Тэгээд утсан нэг дээр нь болохоор твиц дээр зөвхөн англи болон монгол текстийг уншдаг болж ашигласан байна. Тэгээд тэнцэг болгон Монголын нууц төрчөө 20 он болохоор хамгийн бага хэмжээтэй хамгийн жижигхэн дата сэтгүүлсэн. Тэгээд энээр болохоор бид нар бүтэн 12 бодтоос монголын энэ мэдээлэл нь болохоор accuracy буюу наривчлал гэж ноолын нь болохоор алдаан ер нь бол 40 шийдвэр бүрээд наривчлал нь зогсчихжээ. Тэгээд дээрээс нь ансаг болохоор бүр ингээд шулуу явдаг. Энд яг юу болсон гэдэг нь дата сетийн хэмжээний бол бага болсон байна гэдэг юм байна. Тэгээд Google Timer роман дээр болохоор бас 12 баг ашигласан. Тэгэхээр энэ бол Shakespeare-ийн жүжигчдийн зохиолуудтай ажиллах юм байсан. 9 цаг орчим ирсэн. Тэгээд одоо энэ болохоор диалог хийж сурсан байгаа. Хамгийн сүүлийн Propagation дараа гарсан үр дүн дээр гэж байна. Энэ нь болохоор Яванда зохиол роман дээр их дөрүүдийг зураад тэгээд ямар ч гэсэн өгүүлбэр дээр үгдээ алхаа болсон. Тэгвэл нийтдээ өгүүлбэр гаргаж ирсэн байсан. Тэгээд нэр л чөлөөч бид нар медиум дээр бас гитар дээр ууштай кодуудыг текстүүдэд тавьсан байгаа. Тэгээд Монгол улсын хуулиар 314 дээр бид нар сургалт хийсэн. Тэгээд хууль болохоор нэлээд формал хэлээр бичигддэг. Учираас аюул сайн сурсан гэж хэлж байна. Энэ болохоор 80% наривчлалтай хамгийн өндөртэй гарсан. Тэгээд бас ялгаагүй 12 бог сурсан 26 он цаасан. Тэгээд энэ болохоор хуулийг эхлүүлж сурч байгаа. Эхний хэсгийг нь хаваад тэгээд доод хуулийн нот нөө гараас сайн одоо хууль дуусгаж ирсэн. Дараа хуулийн төвд залтуудыг бас дугаар сурсан байсан. Маргааш хэсэг бол шүү. Тэгээд энэ твитэд болохоор бид нэр хэлийг найдлаа. Ямар хэлний текстүүдээр нэлээд гарсан чинь болохоор 95% англи текстүүдээс уусаа англиар монголыг санаачдаг шүү учраас тэгээд энэ болохоор нэг 6 типо интерес болоод Twitter хандлын загварыг гаргаж ирж байгаа. Тэгэхээр дээрээс нь хамгийн их одоо Монголын зорилготой хүмүүсийг гаргаж ирж байгаа. Дараа нь болохоор нөгөө автоматар үсгдэг TQ гэдэг холбоосуудыг бас үсгэж сурсан. Тэгээд retweet хаштаг сурсан. Гэхдээ энэ дээр бидний нэг ажигласан юм болохоор нөгөө TQ гэдэг линк үсгэхдээ жоохон тийм randomized юмуудыг үсгэж Twitter орж байгаа. Богино болохгүй. Тэнгүүд тэрийг яг тэрнээс хойш манай tweet-үүд аюу буруу болсон. Тэгэхээр энээр бас яаж дараа нь өөр төшлөө хийж болох байсан. Тэгээд бидний ашигласан методол ерөөд ингээд анхны асуусан асуултуудаас авахтай бид нар Sony фотографийн дээр баг датанаас бодсон. Дахиад тэрийг ихсгээд Монгол дэвстэй болгож байгаа биш ихсгэж болсон. Тэгээд туршлага хийж болсон. Дахиад дээрээс нь англи одоо read-уудыг бас сургуулж болохоор санагдсан. Тэгээд юуны хувьд буцааж уншихтай болохоор бид нар англи текстээр Shakespeare-ийн транскодуудыг буцаасан сурж хийсэн байгаа. Гэхдээ энэс одоохондоо хийж чадах юм байна. Тэгээд баярлалаа.
Одоо ингээд ирэхэд дуусч байгаа асуултаа ч гэсэн тийм дуусныхаа дараа асууж идэ гэж бодож байна. Манай хоёр багш маань одоо бас өдөө явах гэж байна. Тэгэхээр энэ хоёр байж байгаа. Манай Бинцу дата артист Монгол компани нэрвчлэгийн зэрэг явж байгаа. Тэгээд намарсан.
Арсанаа гэдэг эдгээр дата Facebook гэдэг компани юм байна. Тэгээд юуны өмнө юу сайн зуны сургалтад нэг сарын хугацаанд үрсэг юу маш чухал зуны сургалт байсан гэж байна. Энэ зуны сургалтын зохион байгуулсан Автомобиль багш амгалан самба явуулсан бүх хүмүүстээ ерөнхийдөө баярлалаа гэж хэлмээр байна. Тэгээд зочид ирсэн байна. Энэ болохоор ер нь их олдшгүй завшаа юм болов уу гэж бодож би ч өөрөө анхудаа болцсон хүмүүс. I would like to say it's our great honor to have you here. Гинт англи ярьсан чинь жоо. Тэгээд өнөөдрийн нөгөө шагналт маань болохоор гэрэлтэй ангиллан хоёртой RNA-ийн судалгаа гэдэг чиглэлээр манай компани зүгээс бичсэн дурслын зүйл болоо. Тэгээ манай компани дараа нь ирээрээ ихээр чинь юу гоё юм хэлж байгаа шүү. Тэгээ манай компани бодомод ташаатай гэсэн чинь юу янзлам гэрэлтэй хоёрын хийсэн ажлыг үлдээ уншсан. Тэгээ Propagation гэсэн. Тэгээд юу хамгийн таалагдсан нь нэгдүгээр болохоор яг нөгөө танилцуулсан материал аюул ойлгомжтой болсон байсан юм. Тэгээд хоёрдугаар болохоор нөгөө блог дээр бичсэн бүгдийн уншсаг эхний сургалтыг амар хэцүү. Тэгээ би нөгөө яг ажилтгаар болохоор маань эхний сургалт зураг гэхээс эхний сургалтыг аюул хэрэгэлтэй. Тэгээд өстой жинхэнэ нөгөөд чинь аваад ингээд цэвэрлэл юм хэцүү байсан гэж байна. Мэдээд авах. Тэгээд 5 юм аа гэж цэвэрлэх гэж амар мэдэрсэн болохоор юу сонссон шүү. Тэгээд энэ бэлцэн үеийнхтэй хатуулъя. За баярлалаа. За тэгээд одоо хамгийн их үстэй сэтгэл хатуулаад тэгээд өнөөдөр шоолж байгаа. За үгүй багш нараа гэдэг. Тэгээд би мөрийн дуудаад байна. 자, 얘 아련다야. 이 복수가 있어. 네, 맛있어.